All right. Okay. Cool. So while you guys have been discussing that, right. So to catch up people on video, for one thing, we passed out some food at the beginning of class. Just kidding. I mean, we did, but it's okay. I know some people can't come to class. So we asked people to think about what the difference between a pure and non-pure virtual function was. So yeah, we'll be finishing up inheritance, what we didn't finish from last time, and then going into template classes and concepts. So revisiting the whole idea of templates, but now applied in an object-oriented setting. So very exciting today. All right, so who can tell me what the difference between a pure virtual function and a non-pure virtual function is? Raise your hand. All right, Brian, go for it.
Pure is equal to 0 and non-pure is not.
That's absolutely true. Is there anything else that's different between them?
Like, so you need, your subclasses must actually like define the pure virtual function because like you're implying the virtual function or the pure is different for every class. Whereas with the non-pure, you can say like, oh, here's the general definition, but the subclass can choose to change that.
Exactly, yeah. So to say that louder, in case anyone in the back couldn't hear it, so the difference between the two functionality-wise, so this is the difference syntax-wise. Functionality-wise, a pure virtual function must be implemented by whatever classes inherit the class that you're writing. A non-pure virtual function is you're saying, I've implemented a general solution in this class, but if my derived classes want to overwrite that function, they can. And there's a question actually of, okay, so let's say, so as we saw earlier, an abstract class is just any class that has at least one pure virtual function. In other words, it has at least one function that has not yet been defined. And so we saw last time, yes, an abstract class can also sort of have everything that a normal class does. It can have its own variables. It can have its own non-virtual functions at all. So something like this bar right here. And so a question that sometimes comes up is, wait a second, I feel like I've seen in other places that people actually do override this bar function as well. In other words, non-virtual functions. And I think the appropriate response to that, so overriding non-virtual functions is, it's legal, but it ain't moral. So, yeah, so to clarify, whenever you're designing your own class, if you want your function to be overridable, you want to declare it virtual. And if you want to enforce that it's overridable, you declare it pure by adding the equals 0. Okay, any questions so far? Yeah,
Does the equal 0 do anything aside for just like a notation thing, or is it actually set something equal to 0?
Absolutely. You can think about it sort of as the equivalent of setting a pointer to null. Yeah, it's sort of the function equivalent of that. Good question. Yeah, Brian.
Why do you say like void bar equals return 42?
So that is definitely a typo. Thank you. I was following the equals 0 from above, but thank you for catching that. Yeah, good question. All right, so for a bit of terminology that we didn't cover last time, so we've sort of been using these words up to now, but for an official definition, when we say the base class, that is the class that is being inherited from, aka the parent class or the superclass. The derived class is the class that is inheriting. So we'll see an example later today, but this is just so you know, if you're ever reading documentation on inheritance, base and derived are the terms that you'll most likely see. Okay, so a couple things about implementing your own class and how inheritance relates to, say, like if you wanted to design your own class. So there's a couple things to keep in mind. When it comes to the constructor, one thing that you want to do as just good practice is whenever you're inheriting your class from another class, in your constructor, you want to include the parent class constructor as one of your initialization list arguments. So to be specific, we'll also see an example of this later on, but keep that in mind that when you are implementing your own constructor, you want to call the constructor of the previous class so that you can use whatever constructor it's already created for you. And then if you need to, you can also add on any new variables that you've added in your class. Likewise with destructors, there's also a similar policy. In this case, the key thing to remember when either writing your own class or inheriting from a class is that if you intend for your class to be inheritable, you essentially just always make your destructor virtual. And the reason for this is that otherwise there are some really tricky memory leaks that can happen that aren't sort of easy to anticipate. To give an example, Yes, and in general, whether or not the destructor of a class is virtual is like a good sign of whether it's intended to be inherited or not. So this is why that is the case. So in this case, we have a base class, and we have a derived class that inherits from the base. And the problem is that, let's say a user wanted to create sort of a pointer b of type base to a new derived function. And this whole line is sort of where inheritance gets tricky. Is like, how do you interpret differing inherited classes when you're working with different pointers and different objects. This is exactly what we're skipping in this class. So all of that is sort of like the tricky details of inheritance, which you'll learn in either CS 108 if you take it, or if you read more about it online. But yeah, so we aren't covering that part, but essentially, if we delete B here, we are only calling the base destructor, not the derived destructor. And so any memory that was allocated within the derived class would now be dangling. And so, yeah, so this is the reason for the policy. So those are sort of just two stylistic things to keep in mind in case you ever find yourself writing your own class. Any questions up till now? Yeah, a lot of this is sort of like definitional or just sort of like facts, just like facts spewing out in case you ever find yourself wanting to write your own class. Okay, so another question that people have sort of asked is, what's the difference between private, protected, public? Again, this is sort of just like a bunch of miscellaneous facts all around the same subject. So private means that any of the members or variables that are private can only be accessed by this class. Protected means that protected members or functions can be accessed either by this class or any derived classes. And then public means that it can be accessed by anyone. So to give an example of this, let's say we have a base class named drink, where foo is public, bar is protected, and baz is private. Then that means that drink, the class itself, can access all three variables. Let's say T inherits drink, then T can access both public and protected, and then rock, which is not at all related to drink, can only access the public members, which is foo. Yeah, so sort of more definitions. Are there any questions so far? Awesome. So in that case, just to give you... Oh, perfect. Okay, I think we are back to recording. That's interesting. Oops. So that is for later today. Okay, so let's say... what we're going to do is I just want to demonstrate sort of how to use the syntax of declaring your own classes, say if you wanted to use this in your own code. So again, we saw last time why it is that we use specific using statements as opposed to using a standard namespace. So let's say that we have some class called drink that we're implementing. And sort of the syntax of a class is just as you've seen in any of the header files that you've implemented so far. So you can have a public section, you can have a private section, and let's say in our public section, we just want to keep the default constructor. Let's say we also want to have another constructor where we take in like a string of like the flavor. What flavor drink do we want? And then we would implement that. Let's maintain a private string flavor, and then in here, all we would do, of course, is initialize our flavor variable. And notice here we're using the initialization list that Avery talked about. Oops. Then let's say we wanted to have a pure virtual function. So any class that inherits drink must implement this function called make. What this means, furthermore, is that in, say, our int main, oops, it's impossible for us to do something like drink d equals, et cetera, et cetera, et cetera. And the reason for that is because, and you'll see a compiler complain if we actually finish that, it's because we have a pure virtual function, which means that this class cannot be instantiated. So let's say, because we know that we want this class to be inheritable, then as our good practice is, then we want to declare our destructor virtual. And we'll also make that the virtual destructor. Awesome. Okay. So in that case, let's implement a class T. that will also have some public variables. Let's say it also uses the default destructor. Okay, so based on what we said about constructors, how should we write the T constructor? Sorry, and this should say actually class T inherits from a public drink. How do you think we should write this T constructor? So let's say it takes in a string flavor. What should go after here? Yeah, use it.
The drink constructor?
Perfect. And what do you think is going to be the syntax for that? Trick question. Or rather, it might be sort of intuitive. It might be sort of intuitive. Yeah, so that's exactly right. So all we need to do is just call the constructor that we've already defined on drink using that. Does that make sense so far? Are people following along? Thumbs up, thumbs down.
Can you just run over the line again?
Yeah, absolutely. Yeah, so what this line is saying is it's saying, okay, so we want to define another constructor for this T class because we want to say we want our users to be able to pass in what flavor of tea they want to construct. And so they'll pass in a string flavor. And sort of the one thing that we want to emphasize here is that stylistically, whenever we're creating a constructor of a derived class, so in this case T, then what we ideally want to do is we always want to be calling the constructor of the base class within that constructor. And that's just because the base class already has sort of an interface or like a way it's using the member variables that you want to replicate because you're inheriting from that class. Yeah, that's a good question. And syntax-wise, again, we are using the initialization list from Avery's lecture. Awesome. Yeah, does that make sense? How do people? Yeah, Zach.
Minor syntax question. What was the underscore flavor? What's the significance of the underscore?
Yeah, so the underscore flavor is just a stylistic thing. I could just have easily have called this flavor. And in this case, it would still work because, again, in the initialization list, it knows which one refers to this flavor and which one is the parameter. So yeah, we can actually just leave it like that to avoid confusion. Nice. Yeah, good question so far. Yeah, this was quite a lot of code typed in a short amount of time. So does the class syntax make sense to everyone? Okay, and the unique thing is actually if you take a look at the .h files in say your 106B or X assignments up to this point, you'll notice that it's actually using exactly this syntax. It's just that usually there's so many more functions defined that you don't really notice that like the class syntax and the public and private syntax. Yeah, so what we are doing is we are defining a class within this file. And normally where you would define classes is in their own header file. And so in this case, it just happens to be that we're defining the class in our main.cpp file. Okay. Yeah, does that make sense?
So
Yeah.
generalizing the syntax here. So anytime you want to use some method from the parent class, you just do the colon with the spaces and then call the parent class there? Or whatever method from the parent class.
Yeah, so this colon is just specific to the constructor. It's just for use for what's known as the initialization list. I think it was from 2 lectures ago or something like that. Yeah. And there is a way, say that make actually wasn't a pure virtual function. Say that it was actually a function that had, say we defined it to be like make does like get a cup or something like that. There is a way to access the functions of your parent class using scope resolutions, but we won't cover that. So if you're interested, like talk to us or look it up. Yeah, but that is something that you can do. Awesome. Okay, yeah, and so I guess if we were to continue, so again, let's say that we wanted T to be inheritable. So we could do something like, so again, we would make our destructor virtual. And then again, up here in drink, make was declared as a pure virtual function, meaning that in T, we have to implement that function. And or we have to declare it as a pure virtual function as well and leave it to another function to implement. Yes.
You mean drink and it thinks you mean tea.
Absolutely. I'm glad good test. Yeah. All right. Okay, so if we were going to implement make, let's say So at this point, let's say that we just want to make this the function, like let's say we want all t to be made the same way. So we'll do something like made t from the t class. Perfect, and then that's actually like, like go get a cup, pour tea in. All right, does this make sense so far? So what we've done is we've declared a class called drink, and we've declared a class called tea that inherits from drink. And the four things that we're covering are how does the use of constructors look, how does the use of destructors look, and then how do things like virtual functions get implemented across the two classes. Yes?
In the case of here, what's the purpose of made?
Yeah, so in the case of t, so in this case, since t no longer has any pure virtual functions, we could theoretically do something like tt, and then let's initialize it with a flavor like red. So this would actually also need its own flavor variable. Then what we could do is we could do something like t.make. And so if you imagine this was like another, so a drink and tea is sort of a contrived example, but you can imagine that, say these two classes were the streams class, then this could be like some interface for the streams class, and this could be an actual implementation of it. And so this would actually be something like printing it out to the stream. Yeah.
You wouldn't call drink.make.
Exactly. So in this case, we'd be calling t.make. And the reason is because drink doesn't actually have a make function defined. Yeah, good question. Yes?
Why is the constructor of T also virtual?
Yeah, great question. So why is the destructor of T virtual? So actually it doesn't have to be. I was going to go ahead and declare two more functions that inherited from T, but we may not actually have the time for that. So yeah, I'm actually just going to skip that for now. So yeah, let's say that T is actually sort of the final class, so we don't want T to be inheritable. Then absolutely I would take virtual out. Yeah, good question. And in fact, because of that, I wouldn't even need to write that, but I'll just leave there just for comment's sake. Yeah, Eva.
If make wasn't a pure virtual function up there and you did define it, could you like override it into like you can do in Java, and then you just like differentiate between like calling t.make or .make?
Absolutely, absolutely. So the question is like, again, what happens if we have two make functions, one in the parent, let's say this says like, well, made t from the drink class. Then absolutely, we could call t.make, and in fact, I believe we can actually just run that and see what it prints out. So again, we initialized it with t. That looks familiar. Right, okay. And then prints a milkshake. Quite the make function we have. All right, that's C++ undefined behavior for you. Perfect, and it says made t from the t class. But there is a way, if you wanted to access the make function of the parent class. And the way to do that would be using namescope resolution. So it'd be, I'm gonna have to remember the syntax, but it'd be something that's sort of like drink, or it'd be t.drink make. I think that's right. We'll see if it's right. Made tea from the drink class. There we go. Okay. Yeah. So absolutely. And this is honestly a much longer topic than this. So yeah, I apologize if it seems sort of rushed. Yeah, these are sort of just like some specific C++isms. If you take a look at the CPP reference if you search inheritance and then C++, you'll get to delve into all of the weird, like what happens if you create a class from this but want to access the thing from that, etc. Yeah, so it's definitely a really big topic, and there are lots. Yeah, you guys are asking good questions. Yeah, any other questions before we move on? Yeah, Brian.
Sorry, I don't remember. Could you repeat why it's good to call say virtual destructor?
Yeah, so the reason why we want to call the virtual destructor is because we want to guarantee that, if we go back to here, we want to guarantee that, say if a user for some reason declared, this is going into sort of like the weird tricky details of inheritance, but say like you wanted to declare an object of type derived, but declare a pointer to the object of type base. The virtual ensures that if you say delete B, it will go to the virtual to the derived destructor as opposed to the base destructor.
It's only specific in the case of delete, so you don't really care about the virtual constructor.
Yeah, so it'll be in the case of delete and anywhere else that the destructor is called. In the case, so yeah, the reason why we call why we enforce virtual for destructors is just to prevent memory leaks. So in the constructor, there's in the constructor there's not really like a memory problem. Yeah, and we can talk more. Yeah, if we're confused. Yeah. All right. Okay. Okay. Yeah. Any questions before I move on? No. Okay. So one thing that I mentioned last time was that I gave you guys this problem. The problem was that we had, we had a print statement for the F stream, and we had a print statement for the string stream. And I asked you guys, how would you solve it? And our initial intuition was, oh wait, didn't we learn about templates? Wasn't that the exact problem that they were trying to solve? And absolutely, templates were a perfect solution to that problem. And then I was like, okay, but JK, here's another way to do it. Here's explicit interfaces. So once again, remember, templates were an implicit interface, and these were explicit interfaces. And so a natural question is, again, when do I use each? So it turns out this is actually a larger question of the question, when do I use what's something known as static polymorphism versus dynamic polymorphism? And this is going to be a common refrain in the inheritance section because it's such a big section. I won't go into much of what polymorphism is. You can think of it as basically how the compiler is able to take in different types and use the same code for each type. So it's sort of what you're familiar with from templates. It can use the same template code and choose which template code to use based on what type you pass into them. And so the difference between templates and what we've been covering just now is that templates, you might recall, this was sort of a minor detail, but the way that templates work is that when you write something, let's say that we have a vector template, and then in our code we write something like vector of ints. Then what the compiler will do is at compiler time, it will actually create an entire new template function just wherever we had type name t, it'll literally insert the word int. And so templates are what's known as static polymorphism, where it'll generate all of the real different pieces of code at compile time. In this case, inheritance is actually it's something known as dynamic polymorphism. In other words, in the case of say this, the base pointer b equals new derived, it won't actually know what class you're referring to until runtime, until you're actually running the code. And so there's no such thing as it being able to sort of like be ahead of time, figure out what code works in what places. It'll only know at runtime that, aha, b is actually of type base, even though it points to a derived object. So yeah, no worries if sort of the details of that don't make sense. The general concept to remember is that templates do their polymorphism at compile time versus derived classes figure out all of their types at runtime. And so that's sort of going to be the big difference of when to use each. Yeah, go for it.
Is there a reference to static and dynamic libraries?
Those are going to be different.
Okay.
Static, yeah.
It's the same thing like compile time versus...
Exactly. So in static versus dynamic tends to mean like compile time versus runtime. Yeah, but that's a good question. So as a reference for you guys, if you're ever in a situation where you have a problem like before, you have two print statements, but they're actually referring to the same code and just have two different types, you have two solutions now. You can either create two different classes, or you can use templates. And this is sort of an idea of when to use each. Use templates when you really care about making your runtime fast. In other words, make all the work happen during compile time. And or use templates when, for example, let's say that our two classes were something like, again, like rock and T. In other words, they don't have a common base. Then in that case, our solution of inheriting from the same class doesn't really work. And then, yeah, derived classes you want to use when you want to save on compile time. There's actually one other benefit of using this. So again, to clarify, the way that we're using derived classes here is, let's say we have a class called drink, and we have two subclasses called tea and coffee. Then tea and coffee don't need to define their own main function if the drink one already has it defined for them. So that's what I mean when I say we're using derived classes as an alternative here. Does that make sense? Does that make sense how we're using derived classes here in the same way that we would use templates? Victoria, can you summarize?
I don't know. Okay. So the difference between templates and derived classes for me is the derived classes already has like a function already made, and the compiler doesn't have to like recompile that. But as for templates, the compiler will have to change every template with like the right type.
Yeah, absolutely, exactly. So, exactly. So for the templates, the compiler will have to create every type. Versus in classes, there is only one function. It's just at runtime they have to determine which function to use. And in this case, it is only one function. Exactly. Yeah. So one other benefit of derived classes is that you'll notice that with templates, what's happening is that you are literally copying and pasting the code each time. Just each time replacing the t with another variable type. So it could be that you actually have 6 different versions of the same template in your code, one for an int, one for a double. And from the programmer's perspective, it just looks like one template. But when you compile it in your code, there will be multiple versions of the template. So that's something known as code bloat. And so that's one other advantage of not using templates in this case. That said, of course, we're also familiar with why templates are good to use. So this is sort of another case of like, when do I want to use each? And this is a good reference for that. Okay, does anyone have any questions that they'd like to clarify in lecture? We can also take discussions offline. Okay, yeah, and to give you guys a bit of context, so first, what we didn't cover, so that sort of wraps up inheritance. We didn't cover how polymorphism works, and we didn't cover all those tricky details of like base pointer b equals new derived, like any of those sort of, how do you resolve which function you're referring to? Yeah, those are sort of all of the tricky details of inheritance. And so to give you guys context of just like where to place this lecture, think of inheritance as if you are ever trying to design your own large-scale system where you need different classes of different types. Say like you were trying to design Axis and you needed like a student type and a class type. That's when you want to sort of start looking at inheritance and being like, okay, what types are types of other things? Like, how do I want to structure my overall system? And that's sort of like the entire concept of object-oriented programming, is how do you work with all of these different types, like a student or a class or an assignment, and get them working together. So let's say if your projects that you're interested in working on don't involve that sort of like large-scale system designing, then keep this in the back of your mind, but also don't be worried if you don't understand it. Yeah, so this is if you want to design a sort of large-scale system like that. Okay, awesome. So this is one more slide. I think we've gotten a couple questions on like casting. How are you supposed to cast? I'm actually just gonna leave this for you guys to read later. The TLDR is that with modern C++, the best practice for casting is no longer something like parentheses int b or int parentheses b, as you may have seen from a lot of other classes. The best practice is actually to use what's known as a static cast. So yeah, I'm going to leave that there just as a reference, but I won't go in there now just for the sake of time. But yeah, that's a note on if you want to cast things from one thing to another type. Okay, does anyone have any questions so far that they want answered? Okay. All right. Yeah, that was quite the like crash course in inheritance, especially if you haven't seen it before. So like pick up what you can, and congrats on like all the things that you didn't understand. Okay, cool. In that case, announcements. So assignment 1 grades. Okay, Avery, correct me on this. Have they all been released?
So one section leader had an emergency this week, so
Yeah.
they haven't finished yet, but they will be done grading very soon. Otherwise, I think everyone else's scores have been released.
Yeah, so if you go to paperless.stanford.edu, you should be able to see your assignment feedback. And again, like we would love to sit down and talk through any of the feedback, or if you want to go into your code deeper or like see ways you can make it better, yeah, definitely reach out to us. We'd love to talk about that.
Yeah, and just an FYI, I think out of everyone who's been graded so far, everyone passed. So, yay! Everyone passed.
Awesome. Yeah, so other administrative things, assignment 2 is due today, but remember that you have 4 late days to use throughout the quarter if you haven't used them. And then if you have finished them, congratulations, you have officially finished this class. You've completed all the requirements, and we pretty much promise that you will pass. And then assignment 3 has been released.
Assignment 3, I've put so it has been released. The due date on the PDF is not correct.
Yes.
So I'm gonna change it
Yeah.
now.
Use
But,
the due date.
Yeah, and then I'm also gonna make like one. I'm gonna add one minor note to it because I added move semantics to the assignment, so I'm gonna add like a special note about move semantics. But
Yes.
otherwise, yeah, it's been released already. It's a fairly challenging assignment, but it's also one of the more. I think it's the most interesting assignment. It combines all the topics. It not just combines like topics from the later half of class, but it also rehashes some of the stuff from like algorithms and templates. So yeah, you'll see. Really, you get to work on that assignment. It's a really cool one.
Yeah.
The material goes up to today's material. So Anna's gonna cover template classes. That's gonna cover material for assignment 3. Okay.
Yeah, and sort of logistics-wise, assignment 3 won't be due until after this class has finished having lectures. That said, I know we probably both will still be having office hours, say like the last week if you do want to work on it or just come and talk with us. And then we'll be getting those grades out to you. Yeah, and if you have any questions, post to Piazza as always.
Yeah. Any questions?
So, any questions?
Wait, what's the actual due date? Is it
This, 11/5. Oh, yes, that should be,
It's December 5th. Yeah, it's it's Thursday of week 10.
yes. Yeah, no, actually it's due next year in 2020. So, lots of late days.
Yeah, it's like expiration dates.
Awesome. Okay. So yeah, so sort of one of the last big topics that we're going to be covering is template classes. And sort of the good news here is that you guys are actually pretty much familiar with all of template classes. Not quite, but sort of syntax-wise, it's really similar to what we've seen with template functions. So in fact, just to brush your minds ago, because I looked again and templates were week 4, which feels like such a long time ago. So going back to our STL templates lecture, do you guys remember working with our favorite count occurrences function? Okay, yeah, so to give a recap of what we saw with templates earlier, sort of the logic that we were using was, okay, we have this function that works really well for a vector of ints, but it's making a lot of assumptions. So how can we sort of remove assumptions and put them in a template instead? And so sort of the first assumption that we made was, okay, it doesn't have to be a vector of ints. It could be a vector of any data type. And we were like, okay, that's pretty good. And then we were like, okay, no, we could do better than that. It doesn't have to be a vector of data types. It can be any collection of data types. But then here's where we ran into a problem, which was that not every collection is able, for example, to be iterated through in a linear manner. For example, we saw maps and sets, which don't have this notion of being able to sort of plus in an orderly fashion. And so the solution we found then was, okay, instead we'll be using our favorite iterators to iterate through the function. And then again, this sort of makes one last assumption. Why in fact do we need it to be a collection at all? In fact, we can just use any range of iterators and count the number of times a value appears within that range. Okay, does this look familiar to you guys? Nod if yes. Okay, awesome. So to sort of summarize that, what we were doing with function templates was we were describing how to build a family of similar looking functions. So again, here we were able to build a function that is able to count the occurrences of something within a range of any other things. So it's a family based on the type of iterator you pass in and the type of data type. Any guesses for what a class template is? And in fact, you'll find that the syntax for it is actually very similar as well. So let's actually take a quick look of how template classes work in action. And this is going to be sort of funny because I'm pretty sure, yes, all my code is still in there. Okay, so I'm actually really quickly, oh, don't look. All right, okay, so let's say that we started off with a function, say a class that looked like this. So to give you to give you an idea of what's going on, what we're going to do right now is we are actually going to implement the priority queue that you worked with for assignment 2. Not quite. We actually aren't going to implement the compare function part just because it requires a couple extra details. But what we're going to do right now is we're going to turn this priority queue, which right now only works with ints. It requires that only ints are passed in, and we're going to make it into a templatized class so that it can be a priority queue of any type. So this is a lot of code, so just to quickly summarize what it's doing, we have our main function. We're going to create our priority queue type. Right now, it's only defined for a vector of ints, so we don't even need to do anything like that because there's nothing that we're parameterizing, and we're pushing 3, 5, and 7, and then counting it. And then in our class priority queue right here, so again, notice that we're using this class syntax to define a class. One more time, we have our constructor and destructor. The 3 functions that we're going to implement are the 3 functions that you likely used in your assignment 2, which were top, pop, and drop. No, I'm just kidding, and push. So yeah, don't mind these implementation things. It's actually sort of interesting if you take a look at how the priority queue is implemented in the Stanford library. It's implemented using the way that we've done it here, which is using something known as a heap. But don't mind that. We're actually just gonna collapse that for now. This is our class, and then we've also defined an output operator. So if we run this right now, we're still running simple inheritance. Give me a second. T from the drink class. If we make this our active project,
Click.
I'll just do this one. Yeah. Okay. Unexpected qualified ID. That's right. What do you mean you don't recognize the end comment symbol? Perfect. And it outputs 735. Okay. And the reason why it's outputting it in a weird order is just because the way that we're printing it. So don't mind that. We just want to make sure that it works. Okay, so perfect. So we have these 4 things defined: top, pop, push, and output. And then we have some sort of private variables used to implement the class. So that's the class. And again, what this class is right now, it's only allowed to be a priority queue of ints. So what is your guys' intuition on how we would make this, how we would syntactically make this a templatized class? What do you think we'll be writing? Yeah, Zach.
Do something with template at the top, and then
Okay.
T, call whatever you want for your inputs, and then
Okay. Tell me what to type and I'll type it.
capital T
Just capital T.
or yeah.
What do you need in front of the T?
Type.
There we go. And so this is going to be the first difference. So the one difference between a function template and a class template is actually just the type of the variable that we're templatizing. In this case, it'll be a class. No, I take that back. Sorry. So something that we won't do here, but that you could do elsewhere, is that you can actually make classes themselves a type of template variable. So say that, in fact, let's say we defined another thing like, let's say we defined a struct like node. And then that node had like an int priority and like an int like data or something like that. Then what we could do is we could define our template class over a class. And in this case, we could pass in a node as the type of that. But in this case, we can just stick.
So if you have class rather than type name, does that restrict it to not being like? Does that have to be a class that you constructed?
Not necessarily. So in fact, actually, let's do class. So a class will include anything, including as such as like from the standard library. So it'll include like vectors, things like that. So in this case, since we want to do a vector of a vector of strings, we'll use class. Yeah. Do you have a clarification?
Yeah, because I was thinking about this a couple weeks ago. I think both class and typing do the similar thing. I think there's one edge case where if you want to do like nested templates, so if you want to do a template of a template, then there's some weird things going on there. Most people won't ever write classes which are templates of templates. So for most purposes, the classes and type name and class do the exact same thing.
Okay, that's actually a good clarification. Yeah. Nice. Okay, and so you might remember from the assignment handout, we had something that also said class container equals and then std vector of t. And so what this was saying is it was saying, okay, this class template is taking in two parameters. The first one, which is of class some class T, and the second one, which we're going to call container. And what this is saying is it's saying by default, unless otherwise specified, make this a container of vector of T. Okay, does that make sense so far? Any questions so far about the templatization? Awesome. Okay, so what else do we need to do to fully transform this class into a templatized class? So right now we've sort of declared our template variables, but have we used them anywhere? Okay, so where in our code do we need to change? Yeah, use.
For example, employee install, you would want to push your class file.
Perfect, exactly. So, okay, perfect, we saw an int there. Where else?
You also have to change the constructor.
Great question, do we need to change the constructor?
Because that you have to be able to specify the class type. No.
No, yeah, no, that is absolutely a good question. So in this case, because we're not doing anything special with in our constructors, we can still just use the default. And what it'll do is it'll be calling the default constructor on whatever type we pass in. So if for example we passed in where T is a vector, then what it would do is it would be able to call the default vector constructor. Yeah, good question. Yeah. Where else in our code do we need to modify to fully transform this into a template function, a template class?
In private vector int.
Perfect, exactly. And then there is one more place. Do you see? Perfect, exactly. So in this return type of top. Awesome. Yes.
So, do we want to have a vector T heap or a container T heap? Will we ever have something that's not a vector?
So this vector of T heap is actually is actually not related to the things that we're passing in at all. What this is just the way that we happen to implement the priority queue under the hood. Yeah, so we could have actually chosen to implement it instead as, say, like a linked list, in which case we actually wouldn't be using a vector at all. We'd be using something different. Yeah, so that's a good question. This vector is not related to this vector. Yeah, good question. And so, yeah, actually, that is a good question because it's sort of like we're not actually using container anywhere. It's true in this function, or in the way that we've implemented right now, there's nowhere that we're actually using container. But that is sort of the interface.
Can't you put the container as the thing that's holding the heap?
Yeah, we could. In this case, we could.
Okay.
Yeah, we wouldn't have to, but we totally could.
Okay.
Yeah. Awesome. Cool. So then, in that case, we can now use, so that was it. You guys just templatized a class. So yeah, awesome. It feels very similar to the way that you templatized a function, which is good. And so now we can use it. And notice we've named ours priority _ single letter Q to avoid any weird spelling, because Q is hard to spell. Nah, it's actually not too bad. So as we saw in homework, just to show that our templatized class in fact does work, in our homework we used a vector of strings, and we just did not define. So that's the string.
I think you're missing a closing thing.
Yes, thank you. Perfect. Okay, and so
Different. You might have to put a space because it's reading it as an operator.
Just the name of the variable is not Q, it's
yes.
Q.
Good job, you guys. Yeah, no, good catches. Yeah, so perfect. So in that case, what we're going to do is now the type of the priority queue is it's no longer storing ints, it's storing vectors of string. So let's choose these very arbitrarily chosen 3 words, and let's see how it prints. Right, so this was actually one last change that we had to make instead of invalid
Do like a for each loop over
0. There we go. Yeah, so actually what we would want to do is we would want to do a for each loop because it's a vector of strings. In this case, I sort of cheated because I knew that each one was just of size 1, so we could just access the 0th index. But we have created our own templatized class and used it. So very good job. And that is actually about where we ended. So we have one more minute, so I'm actually gonna try and go through concepts. Because again, concepts we actually went over with Avery way back in the templates lecture. And again, what you guys saw was, right, so when we had a template, there were all sorts of these implicit assumptions that we were making. And so what Avery sort of gave you a sneak peek about was that in C++20, there's these things known as concepts and constraints. So constraints are things right up there where the syntax is, after a template definition, you say requires, and then you provide a sequence of booleans. And in that case, and just for terminology, a concept is a named set of these constraints. And so what the concept does in C++20 is that it allows us to turn those implicit interfaces into explicit requirements. And so now, if you were to try and run this code at compile time, if the thing that you were passing in does not have, say, an input iterator, then your code will actually throw an error saying, okay, I don't even need you to run this. I already know this is not going to be successful. And this was really big because now, as opposed to getting sort of really obscure error messages like underscore underscore first doesn't equal underscore underscore last or something like that, with concepts in C++20, you're now going to be getting error messages that look like its type doesn't have input iterator, which is much clearer. So that's sort of the entire idea of concepts. And again, these can be used with class templates, function templates, and even member functions of class templates. So any functions that is defined on a templatized class. And really quickly, the STL has a bunch of concepts defined. So again, these are just sets of named requirements. And what one might look like is something like that. Derived from, requires, is base of, and is convertible. And so again, these are things coming up in C++20, super exciting, and you can write your own concepts. You can use and create your own concepts. So that's sort of like a really brief overview. We probably won't, if anything, I'll devote like a slide of it at the beginning of next lecture. But you guys have finished OOP, so congratulations.
One more thing,
next.
yeah. So next week there's 2 more lectures, Tuesday and Thursday. Please come. I won't be here on Thursday. I always have this tradition where I take a selfie with my class on the last day of lecture, and so that will be Tuesday. Please come if you want to be part of the selfie. I tell everyone, if you're not in that photo, I won't remember you. Okay, if I see you on the street, I'll ignore you. All right, and yeah. So I think I had 2 sectionees who were in this class and they don't come anymore. So I don't.
So he doesn't even remember who they are.
All right. Anyways, yeah. Make sure you come on Monday. No, Tuesday.
Yes.
People in the video, please come on Tuesday.
Awesome.
And yeah.
Have a great weekend, you guys. Take more jelly if you want it. Yeah, and see you for the last 2 lectures.
Thank you.
What are your thoughts for
Yes.
I'm just wondering if you could have any advice. I have a coding interview next week. I was wondering